So. I know, you know, people have stuff come up.
And making it your life happens.
Yeah, especially when it's a commute. And,
Oh, yeah.
and I'm not sure if, she was ready to transfer this year anyway, so I don't think taking it next year was gonna affect her any, so.
Yeah.
Anyway,
Stuck here too, right, for next year.
I'll be here next year too, I'm not going anywhere. All right. So we'll talk about David's question and when he gets here or after break or something. Did I mention pharmaceutical chemistry in one of those slides?
You did.
So I need to take that off because I've looked into it and the binding affinities and things like that requires it requires running certain programs on your computer that I don't know how to troubleshoot because they're Linux based.
Oh,
And I can handle Linux if it's pure Linux, but Linux on a Mac or on a Windows shell, especially one that I don't have admin privileges on,
that's
is
true, yeah. I didn't think about that, but I was just throwing it as an idea.
no, I like it, and I think it would be a good topic for your final project. Find a couple papers talking about the basics of how they do that and presenting that as a cool, because it is cool. It's not, especially once we do some labs on ab initio. Calculus ab initio is from the Latin, means from first principles.
Oh, that's a good definition.
Ab initio means basically that you're actually doing it from the quantum and nothing, there's really nothing empirical other than stuff like the charge of an electron and Planck's constant and speed of light are the only empirical things in it. And so it is the most computationally rigorous not in terms of its tricky, it is that too, but rigorous in the sense like there's the fewest assumptions made. But it also is the most computationally demanding, and it does, so you can't really use the methods that we're gonna start with. Once you get past about, if you had a supercomputer, you can get to maybe 20 atoms, 20 heavy atoms. Much past that, and even supercomputers will start to get hung up on the calculations. Because the way that most ab initio methods work, that the most efficient ab initio methods scale as n to the third. But the ones that get used most often are n to the fourth, where n is your number of electrons. So, and that means if you double your number of electrons, if it scales as n to the fourth, if you double your number of electrons, your computation time increases by a factor of 16.
Oh, Jesus.
And that happens every time you double. So it's every time you double, it's 2 to the 4 times more computational power required. And so they're very quickly, these don't scale in a way that's actually sustainable. Like, and it's not even like a computational limit. I'm not sure that there will ever be a time when you could actually apply these methods to like a protein, where you're talking about hundreds of thousands of atoms.
Right.
So what they use other methods for things like proteins. So you can use these ab initio methods a little bit, but you're basically using like toy models where like we're gonna ignore the rest of the protein and just look at this binding site's 10 most important atoms and how that interacts with this target molecule. But it's not going to give you great results because you're making all these assumptions in order to do that. Yeah. And so they use what are called semi-empirical methods.
There was I was gonna ask you about the Hartree.
Yeah. Okay.
I don't know what the guy's name was.
Hartree and Fock.
Yeah. What theory or whatever, because I couldn't find anything that said online about it, but it said, well, at least AI said that would be one cheap way to generate potential. So
Hartree-Fock methods score or they scale as n to the fourth.
They are ab initio, they are strictly speaking very rigorous. They still don't give you great answers though.
Right.
Because all we can really do is we basically, if we're sitting up, if this is what the potential energy surface looks like for a molecule for the orbitals, not even moving the atoms around, just the orbitals. If we start right here, up at on the edge of the potential energy well, basically what happens is these methods say, okay, well, if I start with these constants on these atomic orbitals, I get this energy. And then it tweaks those constants to see if it can get the energy lower. And so sometimes that means it goes right here and it just sort of gets closer and closer to the bottom. And sometimes it means it jumps all the way to the other side and kind of like zooms in back and forth. But the problem is we can't actually ever get to the very bottom of these potential energy wells because we're neglecting entropy by doing this. We're only looking at the energy of the orbitals, not entropy. And there's a couple other pieces we're missing where basically we can never get the true value. And Hartree-Fock is limited by that.
Okay,
And
so
there's
I
a
do
couple
like
other
calculus to that at the theoretical bottom of the well.
So if you do that, then it's not strictly speaking ab initio anymore because you're making an assumption that this thing is parabola shaped, which isn't necessarily true.
Variables, you're making the assumption that it's gonna follow.
Exactly. So computational methods inherently are limited both by computational power and by the fact that in order to even get those answers we're still making some assumptions, even if it's an ab initio method.
Right.
So they start using other methods to approximate these larger systems. Get rid of this brown one because it doesn't erase well. So these basically ways that scale better and are cheaper methods. These are actually methods that you can actually run. You're looking for D105.
Thank you. One of those ones I thought when I switched back.
No, Mindy's over there. So these are actually methods that actually will run on a laptop. Even a laptop when I was in college, we could run basic semi-empirical calculations on my laptop. They're not very good answers, but they'll give you answers.
Right.
And so for larger systems, they're a decent way to compare things. As long as you know how they work, semi-empirical methods and molecular dynamics are ways to sort of get an okay answer, but they're using a lot of measured numbers. The reason these are called semi-empirical methods and molecular dynamics are pretty much entirely empiricals. They basically just treat all electrons just as electron density, and they're only looking at positives and negatives. They don't take into account orbital overlap. So like they can't do anything but the Diels-Alder reaction. They'll give you an answer, but it's going to be really wrong because orbital overlap is way beyond what they can actually calculate.
Because that's at the quantum level.
You need ab initio for
Yeah,
that.
you need ab initio.
So these methods are what get used for things like pharmaceutical design because they can simulate an entire protein, but they simulate the entire protein by just saying there's a whole cloud of electron density that's going to be attractive to a positive charge. They ignore the quantum side of it basically. So those are, again, looking at applying either of these methods and how they show up in actual research now. I would actually be super interested in knowing what current technology is because I follow along with ab initio stuff pretty well because that's where my wheelhouse was in grad school. But I don't know much about what's been going on in this area. So that would be kind of fun for me too, for you to catch me up. As part of your project at the end of the quarter.
That's a very good idea.
Yeah, and I have some textbooks that you can borrow that are one that's a decent overview of how these methods work, and one that's super math heavy. Like if you really want to get into the abstract linear algebra, multivariable calculus with imaginary numbers side of things. I've got
got just the book for you.
I
It's-
might wanna read that, honestly,
Yeah.
Doing that, I was,
Um,
the weekend I was looking at Schrodinger wave equation.
Yeah,
I appreciate that.
so that is the only one we can solve analytically. We can solve that one by hand because it's one electron and one nucleus.
Is there anything measurable that can come out of that? So I talked to Kathy.
Yes.
Yeah,
Well, so the hydrogen emission spectrum. The wavelength of light that you get from hydrogen emission spectrum, you can actually trace back. You remember that Rydberg equation that was like the
that's.
one over the wavelength of light is equal to the Rydberg constant times 1 over n squared minus 1 over m squared, where m and n are the different energy levels.
Yeah. Things that tend to go.
This equation is a direct result of the one electron Schrodinger waveform.
Okay.
So you can actually get to this by doing the derivation. That's like a third year chemistry major, upper division. That's pretty standard exercise when you take physical chemistry. As a major.
That's
I was
sort of what I was
looking-
approaching.
Yeah,
I was looking at the textbooks for UC Davis and their P10.
I was gonna tell you you're in the wrong classroom, but
Yeah. What should I say? What's up? I was looking at the UC Davis P-Chem textbook and they had that. The Schrodinger wave equation for hydrogen, and then the next chapter was like.
and then
now-
we can't do
now we
anything
just
with
can't
it.
do anything with
Yeah,
Yeah, this was a full breakdown of the full 4 quantum numbers, and it gives you an n equal to 3, where
yes,
the L can be up to.
but only for one electron systems. As soon as you introduce a second electron, and so one electron can still go to all those different orbitals and energy levels. And you can calculate those different orbitals and energy levels using Schrodinger's equation, and you can do it by hand. Even, it's nasty math, it's, pages of algebra and calculus. But it's doable, but the second you introduce a second electron in there. Everything goes out the window, because having 2 electrons means 1 electron is affecting the energy levels of the other electron. And the nucleus is affecting their energy levels, so you have a 3-body problem. Except it's a 3-body problem, it's even trickier than a 3-body problem with gravity.
Right.
At least gravity is only one force.
Now we're talking.
Now we're talking quantum mechanics and electromagnetic force with the 3-body problem involved as well. And that's why we start using that's why we start using computers for it, to just approximate it, because we just don't have.
There was some workaround. For the 3-body problem.
So the way that we do it is basically you take turns, it's called the self-consistent approach. You take turns treating all the other electrons and the nucleus as one field. So you don't treat them like they're individual charges anymore, you just treat them like the average charge.
Okay.
They call it the self-consistent approach, so you basically say, okay, electron 1. And then everything else is just an average. And what's the effect of the average on electron 1? And then when you set electron 1's energy, you look at electron 2, and now electron 1 becomes part of the average. And you just go through all the electrons until you start getting the same answer twice in a row. Once you get the same, it's basically glorified guess and check. And once you get the same answer twice in a row, you can say, okay, well, that's the lowest energy I'm gonna be able to calculate. That's the closest to the bottom of that parabola that we could get. It's not the real value, because we had to do it by using glorified guess and check. But it's a value, and it's in the right ballpark usually, if you're using the right methods for the right system.
Excited what you guys.
Yeah, it's
There's something, but Kathy just said that I just need to measure something.
so computationally would work for her.
She said, I mean,
Okay.
measures, and I was like, okay, like if I can measure heat transfer, well. wavelength
So
or something.
measuring a potential energy, so calculating your own potential energy surface using some of these ab initio methods, we're gonna do one that's just the rotation of 1,3-butadiene.
Okay.
But we could come up with another system that you can measure potential energy surface, that could work. And then your project would then be explaining this method to the class, and then, and here's what we did, it's a project where the project is actually the method more than it is the results.
And I can apply at least, some lower level calculus to it.
Yeah.
That's.
You could talk about potential energy minimums, maximums, and slopes and things like that. Yeah, that could work.
Yeah.
And we talked about computational methods long enough that David got here for. Break, but, so we're gonna talk a lot about electron donating and withdrawing groups, if not this lecture, next lecture, because they matter a lot when it comes to talking about, electrophilic aromatic substitution is basically this whole chapter. Aromatics have 2 chapters in the textbook that I originally wrote the curriculum from. The first one we've already gone through. It's just that here's what aromatic is, here's a couple basic reactions, here's how resonance factors in. The entire next chapter is electrophilic aromatic substitution. And electron donating versus withdrawing matters a ton for how that works, because it turns out where you put the charge and where you resonate those charges in your intermediates makes a big difference. And in general, what we'll see is the more strongly electron withdrawing something it is, the more dominant it is in terms of controlling things. So you're always going to give priority, and I'm trying to make sure I don't misspeak. Because I am going from memory a little bit on that one. I believe that the more strongly electron, basically one way or the other, I'm not going to commit to it because now I'm second guessing myself. One way or the other, it's either the more electron donating or the more electron withdrawing is going to kind of control everything and have the more dominant effect. And I believe it's the more strongly electron withdrawing is also called a deactivating group, and the more strongly deactivating groups wind up being more important than the activating groups.
So you just wrote there LTCC.
They because they pull electron density away from the aromaticity. But again, hold that thought until after break when I can make sure that I'm not misremembering things. I didn't look at everybody's answers yet, but I figured we'd go through this. The quiz questions, I looked at everybody's quiz questions, obviously, but haven't looked at your answers yet. This one wasn't too bad, right? NBS and heat gives us what? What type of reaction are we looking at? Like bromination, or in this case, benzoic bromination.
Yeah.
Same approach though, right? And then, so then we're gonna get an intermediate that looks like. Both enantiomers. Although technically that's not gonna matter for long because the next step is gonna do what?
I'm gonna eliminate.
So regardless of whether it was R or S, next step, we're just gonna eliminate it. And actually, we have only one possible product in this case. It would be the Hoffman product, because that's our sterically hindered base.
Yeah.
But
Oh, but
we can't put one there. So any base really will work for this. We just want a base that's not a very good nucleophile to try and minimize the substitution product. But if I said NaOH there, yeah, it's still the same thing, especially if there's heat added. You get really into the computational, the ab initio stuff too. As I was erasing that, I was thinking about, so the better, quote unquote, more better computational methods, and put better in quotes because they're more accurate, but they're also more limited.
in how much you can use them because they're so expensive computationally. They scale as somewhere between end of the 8th and end of the 12th. So the best, so now you're talking, you double your number of electrons and it's 10 to the, or it's 2 to the 12th times more expensive. In those kind of methods, you're like limited to, I can do this with 10 electrons. Basically you get 3 atoms. Is all you can do for some of those, unless you have a full supercomputer to work with. Anyway. What was our mechanism for our Birch reaction? What was the first step?
What's the radical, the sodium?
Yeah, remember sodium is a radical already. We don't usually think of metals as being radicals, but sodium, by definition, where it is on the periodic table, has 1 electron to give. And it does so by adding it to one of these carbons. We're gonna wind up with our R groups, or those are electron donating, right? So they're gonna stay on, the pi bonds are gonna stay between these R groups. So sometimes with these ones where we add that electron winds up making a difference, and sometimes drawing out the product is actually helpful in figuring out where to even draw that intermediate. So our final product is gonna look like this, right? That's the only place we can put the pi bonds where all 4 of our alkyl groups are satisfied. So we're gonna add our electron, wherever we add our first electron is gonna be one of the sp3 carbons. So we want to add it either here or here, it doesn't matter which order. But we start by doing that. And then we wind up with a bunch of single barbed arrows. And it seems like we wouldn't really necessarily need to draw all of those. But if you don't draw all of those, you wind up with your radical and your negative charge on the same carbon, which can't really happen. That's actually 9 electrons on that carbon. So in order to avoid having 9 electrons on one of the carbons, you've got to put your radical on one side and your negative charge on the other. And the way that this is drawn, you get the negative charge at the top, your radical at the bottom.
Say there was an electron withdrawing group on one of those sp3 carbons, where would the electron go then?
I think if I remember from the last lecture, the electron withdrawing does take the priority.
Yeah,
Yeah. And
so
so
I'm just trying to think of where you would put the negative charge versus the radical. It wouldn't matter for the final product, as long as your final product, your electron withdrawing is on one of your 2 sp3s.
oh, right.
I'm thinking about for this one, I think you're gonna wanna put your electron withdrawing group where the negative charge is, or the negative charge where the electron withdrawing group is. Because you don't wanna put an electron withdrawing group on a radical, because that's pulling electron density away from it and making it less stable. Electron withdrawal or radicals are more stabilized by having electron donating groups, just like cations. They have the same rules as cations for stability. So any electron withdrawing group would go where the negative charge is in the intermediate.
Sure, it's
Yeah, that makes sense.
That I just had to stop and think about it because I don't want to send you give you generalized rules that wind up being wrong. Next step is just proton transfer, right? So and then we're gonna do the whole thing again because we still have a radical here. So the second step is another sodium comes in, donates an electron to the bottom part.
touchscreen, so
I don't know what that was. You know what, Teams has been pushing updates at. And I wish we didn't have to use Teams here, but. The Wi-Fi or the cell coverage in here being what it is, my wife and I use Teams to communicate across campus because we can't rely on our cell phones. Yeah, so once we get here, that's gonna give us. Sp3 carbon. Not a negative charge yet, that's still radical. Then we're gonna do the same thing. One electron donated from a sodium, followed by a proton transfer. So the trickiest thing really about the Birch reaction. Is one, that it's kind of like a combination of a free radical mechanism and a standard mechanism. And two, just figuring out where to put those, the intermediate, what does the intermediate look like?
It's a, what is the electron withdrawing group, the priority would go. for the-
That's what we said last time. Guys, still, but generally speaking, the electron withdrawing groups are more strongly electron withdrawing than the donating groups are donating. So in general, I tend to give priority to the electron withdrawing groups, but again. We should double check that.
That is the case on this one, you could, if one of those were changed to an electron withdrawing group, you can raise the double bonds such that two of the electron donating are on
Right.
the system of the electron withdrawing.
Right, exactly. You always want to satisfy as many as possible, but if you can't satisfy all of them, make sure that your electron withdrawing group gets satisfied and then
Yeah.
take care of everything else the best you can. All right. So let's talk about electron or electrophilic substitution. We already know we can't just do addition reactions when it comes to aromatics. So regular alkenes, even conjugated alkenes. We can put through regular electrophilic addition by using bromines or other halogens, right? But we can't do that with benzene because we wind up breaking the aromaticity to do that. Basically, we're not really gonna break the aromaticity, Birch reaction notwithstanding. We're not generally gonna break the aromaticity unless we're making a lot more resonance some other way, which is pretty uncommon. But what we can do, what does wind up reacting is we have all these electrons here. We can basically replace a hydrogen and put it through a substitution mechanism. It's not an SN1 or SN2 mechanism because those are nucleophilic. And these are gonna work by, because you have all this electron density, they're a totally separate beast. Right, and so what we do wind up seeing is if you tried to, basically what they found when they tried to force benzene to go through an addition reaction is instead of making the dibrominated molecule, they made bromobenzene. Right, and so they eventually figured out that this is so kind of by definition, it's not an electrophilic addition, it's an electrophilic substitution, and it really only happens with aromatics. So hence electrophilic aromatic substitution. And basically the only substitution that we see in these reactions is we substitute and replace hydrogens. We don't have a leaving group get replaced with another leaving group. We get a hydrogen replaced by what we would normally think of as being a good leaving. All right, and so that we'll talk about the mechanism in a second, but the most common electrophilic aromatic substitutions. We can halogenate a benzene, we can make bromobenzene and chlorobenzene. We can nitrate a benzene to make nitrobenzene. We can add a sulfonate group. Then these last two are not as, their yields are not as good, but they're really helpful synthetically. And so for that reason, and they are named reactions as well, and that, you know, standardized tests, they love to pull named reactions. They're named typically because they are important. So these are Friedel-Crafts reactions. Which is spelled. It's Friedel, yeah. And Crafts is easy.
And those are the R and the ketone.
Yeah, so this is the Friedel-Crafts alkylation. You're adding an alkyl group. And making the ketone is an acylation. Because adding this that's considered an acyl group, ACYL. And again, we'll spend more time with those here in a second. The nice thing about these is that all of these electrophilic aromatic substitutions, they have the same mechanism. The only thing that really differs in these is the way we make the electrophile. Because electrophiles are not inherently as stable as nucleophiles. And so we have to generate a strong enough electrophile that it can actually temporarily disrupt the aromaticity. And then we let it reform the aromaticity. But in order to do that, we have to have a pretty reactive molecule. And so that generating the electrophile winds up being the only difference between these. Once you generate the electrophile, they all look the same. They all go through the same intermediate, which is called the sigma complex.
Yeah, it's like I imagine for the Friedel-Crafts alkylation, you would need like a carbocation, right?
Yeah, that's basically what you do is you generate a carbocation, and your carbocation acts as a electrophile.
And that's gonna want to react with anything though.
And then you have to worry about rearrangements too.
Yeah.
So, and we'll wind up saying this is a lot more stable and predictable of a reaction because our intermediate for this doesn't go through rearrangements and winds up being a lot higher in yield. So as much as we can, we use acylation. But again, more details in a second. So the bromine is where they first discovered this. So we'll start with bromine. Also because we understand bromination as a mechanism, right? This is a review back from early last term, right? You have bromine reacting, you make this bromonium ion, and a bromine leaves, and then your bromide can act as a nucleophile again. However, when benzene, so this is bromine acting as an electrophile in some regards. It's reacting with that pi bond. So you have bromine gas or bromine SBr2 acting as an electrophile, followed up by bromide acting as the nucleophile in this case, right? But bromine is not a strong enough electrophile to be able to do the same thing to benzene, even temporarily. So to make it a better electrophile, we need a Lewis acid. So Lewis acid is one of those terms that we defined all the way back in Gen Chem, and then we never touched it again. Did some arguing about it. It does show up a little bit because Lewis acids can affect pH, right? So when you're talking about equilibrium back in Gen Chem, there was there were a couple cases where you can make those complex ions form, and that winds up changing your pH a little bit. But OChem is where Lewis acids really wind up playing a role. And so normally we think of acids are Bronsted-Lowry acids. We think of in terms of protons, an acid's a proton donor, a base is a proton acceptor.
Lewis acids and bases, you just flip the charges, so you also flip acceptor versus donor. So Bronsted-Lowry acid is a proton donor, so Lewis acid is an electron acceptor. It's sort of like multiplying by -1 twice. You flip the charges, so you also flip acceptor donor. Right, so the Lewis acid, it's not immediately obvious how it could act as an acid in this case. It's really just an acid in the sense that you put it in water, the pH changes. In the way it works, so to generate electrophiles is by donating electron density to the iron, you're pulling electron density away from one of the bromines. Bromines don't like that. Bromines are electronegative and they need to gain electrons to be stable, right? So by pulling electron density away from the bromines, you generate something that looks a lot like, it says this is an equilibrium arrow, but you're not going to have very much of the free bromine with the positive charge. So this is going to be like a very small forward arrow and a very big backward arrow, but you generate some small amount of this positively charged bromine ion, which, as you can imagine, is really unstable and really good at finding electron density and reacting with it. Right, so this step of the mechanism is just electron density goes to the iron, electrons get pulled to make the tetrabromo iron and a bromine positive with a positive charge. So then when you have a bromine with a positive charge, and sometimes we just draw it like this. So we don't always just draw it as the bromine with the positive charge because that's so unstable and uncommon. Even just drawing it like this, you can still show what's going on pretty well. If you have a benzene, this pair of electrons is being pulled to the bromine that's directly attached to the iron. I didn't mean to draw that towards the lone pair there. You basically just get that bromine being attracted to to one of the pi bonds from benzene, which is going to make an intermediate that looks like this. Right, because we pulled electrons away from one of the adjacent carbons to make a new sigma bond. And then that's going to have, no, actually switch to hydrogen and bromine here. That's going to have a few different resonance structures, right? Carbocation with a bunch of conjugated pi bonds. So if these electrons move over, get a positive charge there. Bromine and hydrogen are still in the same spot. And then you can do that one more time, right? This whole intermediate are these three resonance structures collectively are known as the sigma complex. Sigma because we made a new sigma bond. At least I'm assuming. That's how I remember it anyway. Right, and so all of these
electrophilic aromatic substitutions. You generate an electrophile. Your electrophile breaks a pi bond and makes a new sigma bond, sigma complex. And since we already know what the end result is going to be, what's the next step in the mechanism?
Basically, the bond that some of the hydrogen goes over. Yeah.
Yeah, you take off hydrogen. It's really more like of just a proton transfer. And in doing so, when you show that, and usually you have it drawn with the whatever your Lewis acid is. That you used to generate your electrolyte in the first place can act as a base, and it's gonna your proton is basically gonna jump onto your Lewis acid. Or one piece of it. All right, so clean it up. So other than generating the electrophile, it's really just a two-step mechanism. It just has that resonance in there, and that resonance gets more important when we start talking about doing this to a benzene that's already substituted. Because the different resonance structures, putting the charges in different places in that sigma complex, where you substitute, which hydrogen you substitute, is going to depend on what your substituents are that are already on the benzene ring. Are they electron donating or withdrawing?
And there I mentioned, as far as the two significant structures, it would just be the two terminal ones. So the one in the middle, you can't eliminate the hydrogen in the form of double bond, right? So that wouldn't, you probably wouldn't see that affecting what the product would be. It'd just be the one left and right.
We will when we, so right now, all the carbons are identical, right? But what we'll see is if we had an R group on one of these carbons. Where the bromine attaches is going to be based on where the R group is. Because if you'll notice, you wind up putting that positive charge when we resonate it around, it's either in the ortho position or the para position. Relative to where we added the bromine, right? So depending on whether we have an electron donating group and an electron withdrawing group, we're either going to put our new substituent, it's either going to go in ortho and para position, or it's going to go in the meta position. In order to put these positive charges where they're most stable. So you're thinking about it the right way. But as long as we're starting from pure benzene, they're all equivalent. And all of these intermediates are the same energy.
Right.
Like, yeah, we're always going to draw our next step, our proton transfer from one of these two, but they're all actually equally stable.
Right.
As far as these resonance, they're all equal resonance contributors that way. And the reason that this works, both the addition reaction and the substitution reaction would both go through a sigma complex or some equivalent to it. The difference is, if you go through the substitution instead of addition, we get to reform our aromatic ring, which makes it our product way more stable. Kinetically, it's actually more favorable to make the addition product, but the difference in energy when it comes to the substitution product means that basically we're going to see none of this.
It's such a small difference in activation.
It's such a small difference here, but it's a huge difference in delta G overall. Exactly. All right. We'll do this one more time before we start looking at the other versions of this, the other electrophiles, because chlorination looks really similar to bromination, except we don't use iron chloride, we use aluminum chloride. Iron chloride would probably still work, but I think it's too strong. Of a Lewis acid. And chlorine's already more reactive than bromine is. So basically, this was probably just, they determined that using aluminum versus iron for chlorine works better because of how the difference in electronegativity between chlorine and bromine. We don't need to make chlorine too reactive, because we don't want it to explode. Right, because that was the reason why we don't use chlorine for any of these, right? It's like chlorine's really reactive, bromine's pretty reactive, fluorine was too reactive. We want to make the chlorine more reactive than chlorine, but not to the point of becoming fluorine. So you could probably use iron, but you probably don't want to. It's probably more dangerous. And aluminum gives us good enough yields. You just think about where aluminum and iron are in the periodic table. Aluminum is a metalloid, right? It's one of the most electronegative metals that you can have. Iron is really pretty good at giving away electrons, so we don't want to put such a giant jump in electronegativity. We want our metal to be a little bit more electronegative because chlorine is more electronegative. And so, with that in mind, me telling you it's the same exact reaction with a different metal and a different halogen, try drawing that mechanism. We'll fold this into our break like we've done before. Take a couple minutes to do this. And we'll take a 10-minute break. So we'll come back at 11. Then I need to go check on something over in instruction based on what I just saw walk over there. So I'll see you back here in 15 minutes or so.
Yeah. For ours to else, for sure. Oh, I went to Ross with my buddy and we just found the ugliest wine shirts we possibly could use as our climate shirts this season. I just felt like wearing it. This is look how hideous this is. Literally says Paul Thomas. Where my fucking spirit. It is summertime,
Damn right.
and then, yeah, the mustache, I just felt like it. I'm like, well, I was gonna cut my beard off. Feel the breeze on my face for once.
Right.
Ray, are you okay?
Pestering me to do something.
I don't even fight it that much, I'm not sure why.
Okay, that's fine. Hey, I'm gonna bring mine up for sure, but try to also maintenance. And then bring it up, I'll bring it up. So, maybe next meeting. Yeah, it's mostly all free time. Still, yeah. Yeah, there you go. We're building some shit up. Oh, yeah. It's awesome. I've also like, we've been, high shop space gnomes. And the most of my shots. Space gnomes is fun. Yeah. Space gnomes.
It's next to Pie Shop.
Yeah, it's on the other side.
It's on the west side. So it's,
Closer to Solomon.
so it's closer to Sawmill Road.
Okay.
So you go off, there's a little spot that you go off the road. Why have you been flying out there, dude?
So this one, I don't know what they're called. This one, that was hard. You start with. I think I know what you're talking about.
Some of those fucking things are like.
Yeah. Yeah, I do, it's my buddy knows this happened. This one was painful. I managed to flash this one, but you start with that finger crack with like no feet. And those were like max, that's like a 3-finger pocket, that's a 2-finger pocket. And then from there you get up onto this. And this is painful. This whole thing is painful.
You just smear your way up, you know.
Where else is that? You know, like, off the Solomon Road, I'll show you, yeah. I feel like Does it say private property? No. No. It's not the same place. So. There's Sawmill, right? Pie shop's like right here. And then. So if you go around here, there's this like little neighborhood. Thing up here, Space Domes is basically like here. Like it's this. Oh, it is. Yeah, that's the same spot. There's another parking lot, way back there, and you're gonna hike in, really far, which is dumb. If you just go on Sawmill Road, there's like a sign that says, it's the do a drift sign. Oh, maybe, there's that sign, you park right there and just go straight up and you find a better spot now. It's just like, it's an overhang with like a shark tooth coming out of it, and it's really fucking nice to even just boulder it.
Where's that?
So right there.
Next to that house.
Yeah, it's like.
Oh, that's just the boulder in here.
Oh, yeah,
That's the stone house.
cause there's
There's a bunch of owners to get rid of this stuff, and we're sending smoke along to it.
We looked into that house and we tried to find the rock, and then the alarm started going off. So we were just like, no, this is the worst rock climbing.
That's really nice. I haven't been up this.
Rock climbing, but it's so long that I
There's haven't been a flat shot in a long time either. Flat shots.
There's so many up there. Yeah, Space Domes is hard, like the easiest one is a 5.9, which was fun. I think that one I showed you was like a. Was that the 5.10?
There's a 5.11. Well,
It's been a lot of years since I tracked down things on the internet to go do tough stuff. It was always surf breaks for me.
Oh, nice.
Oh, okay, the surf's going here. We go up the coast about 5 miles. It cuts out this angle, and then we just have to climb over some barbed wire.
That's the fun of it.
Exactly.
Whole blanket and throw it over.
Right. In your wetsuit, carrying a surfboard.
Yeah. That's one. But that one I'll show you the finger crack, that's a lot of those. Did you ever surf in Hawaii?
In Hawaii?
Yeah, in Oahu?
Not Oahu. I surfed on Maui.
You go right.
So last time I went to the big island, I don't think I got on the search for.
My brother's been teaching, so start on stairs for.
Oh, nice.
Yeah, that's decade almost.
I think people they get super territorial, especially of tourists, in Hawaii, so I try to stick to the more tourist friendly surf breaks in Hawaii, because I don't want to step on any toes.
Even like the tourist friendly ones in Hawaii, or in Oahu, I got like, came up on by like 5 people, like locals, and they were all like asking me what my business was, and I just told them my brother's name, and they were like all backing off and everything. They're like, oh, we know your brother kind of thing.
I mean, for the most part, as long as you're not a dick and you know how to, what the etiquette is.
Yeah.
You know, not to drop in on them and wait your turn in line and things like that,
Yeah.
most people. But there are some areas of Hawaii in particular that are really territorial.
It is.
Yeah, there's a lot of similarities, because there's only so much, like, there's so much rock out there.
Yeah.
How you get territorial about it, but there's good rock. And
Yeah,
there's
there's
other
rock and then there's, man.
All right.
Probably.
So nothing tricky about this one compared to the other one, right? Generating your electrophile. Gonna look just like the other one. We have aluminum acting as the Lewis base or Lewis acid. Chlorine comes over here. That's gonna give this outside chlorine a little bit more of a partial positive. Just enough that it makes it an even better nucleophile or electrophile than it would normally be. And so then we have, maybe I should have drawn it on the other side for the sake of. What'd you say?
You said it was an outside release positive charge, really.
So as it's drawn in this structure, if you look at formal charge, this chlorine only has 6 electrons that it controls now, compared to 7 on the periodic table. So when it has all of these bonds, that's the chlorine with the positive charge. But really, this chlorine also has a partial positive, just because all of the electrons are being pulled this way. So when we draw the structure, we draw the positive charge there, but when it's actually this one that's gonna act like it has the positive charge. Because that's gonna happen. And with the chlorine in particular, we're really not gonna ever see like chlorine with a positive charge as a free molecule. It'll be this whole complex reacting with the benzene like this. With the bromine, at least some of the time, you might have an actual bromine with a positive charge. Like that was an equilibrium that favors making the complex, but you can have some of this. You're gonna have almost no free chlorine with the positive charge, because chlorine is so electronegative. So it'll sit like this until we make the sigma complex. And again, this is benzene, so all carbons are identical, so it doesn't matter whatsoever where you put the chlorine. It's just gonna make one of those carbons into an sp3 carbon temporarily. And the carbon right next to it becomes positively charged. We get that, which is the sigma complex. It's gonna have those 3 different resonance structures. If we're being really careful about drawing mechanisms, it's good to be in the habit. I know it's takes up more space and more time. It's good to be in the habit of drawing this out, because when we start getting into the substituted benzenes, showing where those positive charges show up winds up being really important. So. Positive charge in the ortho position, positive charge in the para position, positive charge in the other ortho position.
So I imagine when you have other constituents on the ring, like you have an electron drawing one, you want a positive charge on the carbon that is bonded to. So that would be unstable, right? So that's electrons.
Yeah,
Yeah.
yeah, So we have an electron donating group, putting the positive charge where the electron donating group is favorable. And so those are considered activating groups. Because it actually makes the sigma complex more favorable. An electron withdrawing group. Not only do you have to make sure you don't put the positive charge next to the electron withdrawing group, but it makes the entire thing less reactive. It's a deactivating group. And so for your electron withdrawing groups, you're only ever going to see the chlorine add in the meta position. Relative to an electron withdrawing group, because the meta positions never get a positive charge out of these three resonance structures. Alright, so there's our sigma complex. And then last step is just, usually it's the other chlorine that added, in this case, is gonna act as the base. So now because we have AlCl4 with a negative charge on the aluminum. We reform our benzene plus HCl. You'll notice that the aluminum chloride is not actually getting used up. We regenerate it. So it is actually acting as a true catalyst in this case. And the iron bromide as well from the last example. You just need them there to act as that Lewis acid, but it's actually the chlorine and the bromine that are the reactants that actually you need to make sure you have a stoichiometric amount. Obviously, if you have more than just a tiny amount, some catalyzed reactions, you need like a tiny amount of the catalyst just to start things, and then it goes at a pretty good pace. You still do need a fair amount of this. They can, you know, up to a point, the more of this you have, the faster it will go. So it's because of the mechanism, it's a little bit different than you know, say an acid catalyst where you add 1 drop of concentrated sulfuric acid is enough to start the whole thing. Or shining light on a free radical reaction for 10 seconds is enough to get the reaction going. But it doesn't get used up, which is useful. We can get away with having a lot less of the chloride. Are you gonna do 2 student workers? I know Jerry, you're a tutor.
Yes.
Yes.
I'm enrolled as a tutor, but they haven't been doing it's at 8 hours, so.
You might still qualify for a free lunch there.
Check your email because they sent an email out.
Student worker appreciations,
Do you know what the food is?
Subway, I think.
That's not bad.
Yeah, they're-
Isn't FDA legally red? They have to call it red light.
Bread like.
Red's like. It's a red light substance.
What makes it not red?
The FDA, I'm not the guy.
Was it, were you the one who was telling me about Velveeta's, or American cheese? Who was telling me about,
We spoke about American.
what was the, how do you make American cheese?
It's sodium citrate and sodium hexametaphosphate that act as emulsifiers, and so it's like 70% cheddar, 30% water, and trace amounts of chemicals. It's actually kind of a lot. The chemicals.
So you could probably do it with egg albumin. Or egg white works as an emulsifier pretty well. You could probably make your own American cheese, artisanal American cheese.
It's just so melty.
Beer works really well too. There's a reason they make beer cheese. It's not because the beer is adding flavor, it's because it helps emulsify the cheese and keep it melty.
I mean, it does a little bit,
Yeah.
especially if you use a dark beer, but it's mainly that it
So what's
emulsifies.
the emulsifier? Is it
It's
like
probably some of the,
the
well-
yeasts or like the malts in it or?
it's probably a combination of the salts and the ethanol, at least initially, but then the ethanol boils off, so. That is a good question.
Your cheap beer.
All right, so here's the officially drawn out. General form, where we just have electrophile. Just like we had nucleophile to represent all of our nucleophilic substitution, we have electrophile to represent electrophilic substitution. Generating the electrophile is the only part that's really different about all of the reactions we looked at the beginning of class. But they are significantly different enough that they're worth looking at. Especially as they all have their own specific uses. I do love some of the old school chemistry terms. Fuming sulfuric acid. Because sulfuric acid is not angry enough, this is fuming sulfuric acid. Basically, you take concentrated sulfuric acid and then you bubble SO3 gas into it. So you fortify it with extra sulfur and oxygen. So sulfur trioxide is pretty nasty stuff on its own. And it is a gas, so we don't really want to use it on its own, and its Lewis dot structure even looks a little bit weird. When you look at, it's got a sulfur with 6 bonds. Because remember sulfur's third row of the periodic table, d orbital can get involved. But the difference in size between the sulfur p orbitals and the oxygen p orbitals mean that those pi bonds, even though they're pretty weak. But we can't just generate SO3 on it. So we can't store SO3 on its own, even in a tank. It'll wind up reacting to make oxygen gas and solid sulfur. So we kind of have to generate it. Anybody remember the term for that when you generate the reactants in the reaction mixture?
One pot.
Yeah,
Or in situ.
in situ. So fuming sulfuric acid is a way to maintain your levels of SO3 or generate your SO3 in situ. And you'll notice the difference in the electron density here. The oxygen both being more electronegative and having smaller orbitals means that the sulfur is pretty strongly positive. So we don't actually need a Lewis acid in this case. This is a strong enough electrophile on its own. The trick is just actually making it and keeping it around long enough, which is why we need the fuming sulfuric acid. Right, and this all looks really familiar, right? Let me change the size here so we can see the bottom of it a little bit better. All my slides are not, they're still not really all designed to fit on the screen. During COVID, when everybody was looking at small screens at home, we were doing studying all of the figures as large as humanly possible down there because everybody was looking at a small screen. Alright, so same thing, right? The only difference here is at the end, we make a weak base that's more stable when it's protonated. And so we add the sulfonate group and then we just do one more proton transfer. And since we're in acidic conditions, either just pick a sulfuric acid or just pick hydronium as your proton source, but we have plenty of protons to go around if we're doing this reaction in fuming sulfuric acids. Given that this is the same mechanism over and over again, more times you write this, it should be one of those ones that when you close your eyes at night, you're seeing this figure on the back of your eyelids.
So then these are gonna be two separate steps, I imagine, in order to proton transfer. That would work very well in a very acidic environment.
No, it works really well in a very acidic environment.
Even though the water is becoming a hydronium.
I mean, you could either just take a sulfuric acid molecule, or if you have concentrated sulfuric acid, you also have hydronium. You can't get rid of the water.
Right, it's always convenient.
So,
But it's just the equilibrium will be pushing it very much towards the hydronium already. So to then make more hydronium would be unfavorable.
remember, there's another equilibrium reaction that's generating this from the sulfuric acid.
Yeah.
So as you use this up, you just regenerate it from the sulfuric acid.
So I guess I was looking at the step previous. Where it's a water molecule.
Oh, something acting as a
It's
base.
hydronium ion.
No, just because you always have a little bit of both of these around, you always,
Works, yeah.
like, there's gonna be less of something to act as a base than there is acid, but there's still something around.
Okay.
We'll see in the next one. We can make some really, really strong acids by mixing together other strong acids. But even those still have some amount of base floating around. Even if it's a, 10 million to 1 ratio, that's still enough that there's something. Speaking of extra strong acids, does anybody know how you dissolve metallic gold?
They call it the piranha solution. right?
There's one, that's the useful way of doing it.
Complex?
No, it's called aqua regia. Which
Oh, aqua regia, okay.
aqua
that's not-
regia in Latin literally means royal water because it can dissolve gold. And it's a mixture of strong acids. Get concentrated sulfuric acid, and I would think aqua regia is concentrated sulfuric and concentrated hydrochloric. In like a 2-to-1 sulfuric to HCl ratio. And it'll dissolve just about anything. But it's also one of my favorite stories about scientists acting both politically and as anti-fascists. During World War II, when Germany was invading, I think it was Denmark. There was a Nobel Prize winner in Denmark who didn't have time to go to his lab to get his Nobel Prize before he evacuated ahead of the Nazis. He just had to leave in the middle of the night, leave everything behind. And a Nobel Prize is a big old medal that's made of solid gold. And so very understandably, his co-workers who were not Jewish, they were sticking around behind, they weren't evacuating, and they took his Nobel Prize and they dissolved it in aqua regia. And then they put it in the stockroom, they labeled it properly, they put it in the stockroom as a solution, and they left it as a solution until the war was over. Then they reprecipitated the gold back out by neutralizing the aqua regia and got metallic gold powder that then they recast back into a Nobel Prize. using the same atoms.
So the Nazis couldn't sell the gold to Switzerland.
If they-
I know.
Yeah, that was a big thing. They hoarded all the gold that they
hoarded
could steal from the populations they invaded. And obviously a Nobel Prize, that's a lot of gold and also like a lot of like clout and prestige, so. Yeah, they just labeled it properly, put it in the stockroom, just left it there for a couple of years. This version is not technically aqua regia. I think it's worse. This might be the Piranha solution.
I think so, yeah, I think this is what I was thinking.
It's nitric acid and sulfuric acid.
Messed up, man.
You know, because sulfuric acid has a pKa of like -9 for this first proton, and nitric acid's like -3. They're both strong acids in water, but we can actually force the nitric acid to act as a base. We can protonate nitric acid if we put it with sulfuric acid. Which then we wind up making this, goes through a leaving group leaves, and we might make nitronium. Nitronium is just NO2 with a positive charge. Normally NO2 is really unstable because it's a free radical. This is NO2 with a positive charge, so it's no longer a free radical, but it is an exceptionally strong nucleophile. I believe, I heard this anecdotally, I don't know if this is true, but I believe that they call it the Piranha solution. Because it's a case of, there's always a bigger fish. Nitric acid is a pretty big fish, but put it with sulfuric acid and it looks like a pretty small fish all of a sudden. And then we do the same thing again. Nitronium is your electrophile. Make a sigma complex, draw your resonance structures. Find something that can act as a base. And as we can see, it can be just about anything. Anything with lone pairs will act as a base in an acidic enough solution. Especially in the case where we're trying to reform an aromatic ring, there's a lot of thermodynamic driving force to push that proton onto something else. All right, so I'll leave the rest of the mechanism. The rest of the mechanism is left as an exercise to the reader. Is that if you run into that in math textbooks yet? The math textbooks famously will say the rest of that proof is left as an exercise to the reader. They'll just tell you that something is true, and then they'll start the proof, and then just say, you all can figure it out.
They'll do the miracle step.
Exactly. Which is not as bad as Fermat's last theorem. You heard of, I don't remember what Fermat's last theorem is, but it's something that he was writing back and forth to one of the other mathematicians, and he wrote something like, here, or this is true, and I can prove it. I have written the most glorious proof. And he like wrote it in the margin of a letter he'd already written, and he didn't show the rest of the proof, and then he sent it off, and then he died.
Yep.
And so for like 150 years, 200 years, nobody's been able to prove Fermat's last theorem. He says he proved it, and he was really pretty accurate about that. But nobody else has been able to do it since.
Or didn't he know that he was gonna die? Yeah, since people have no idea when he died, so.
That would be even better. I don't think so. Because then we really couldn't trust it. But the thing is, we haven't been able to disprove it. Every time we use Fermat's last theorem, we can't find a set, it has to do with the set of integers and how they work as factors with each other and to find the next largest prime. And we have not been able to find a prime number that is not covered by Fermat's last theorem. So it looks promising, but we can't prove it yet.
Right.
That guy.
And as we talked about before. Our acylation and alkylation, acylation. Works just like we were talking about, if you have a chlorinated. Alkane. And you put it with aluminum chloride, we get the same sort of effect happening, except. Instead of generating a chlorine positive charge, we generate a carbocation. But as we're aware, carbocations do have a tendency to rearrange themselves, so we can't rely on this to attach the alkyl group in the same way necessarily. If there's a way it can rearrange, and it doesn't even rearrange predictably though, because we wind up making this intermediate. It mostly stays like this. But there's an equilibrium where it actually dissociates and you get the carbocation. And that, so because it doesn't 100% of the time generate the carbocation, it doesn't always rearrange. It sometimes rearranges. So if there's a possibility of it rearranging, you're gonna get a mixture of products. Not always in a predictable ratio. You can predict what the products are gonna be, but not necessarily how heavily you're favoring one over the other. So, plus you don't get great yields. This is a okay electrophile, but it's actually not that good of an electrophile compared to the other ones we've been talking about. And so it does have a tendency to give you pretty mediocre yields, like sub 50% yields. The acylation, on the other hand, doesn't rearrange. Because it has this carbonyl, you're always going to make this acylium ion. And that won't rearrange. Putting the positive charge on the carbon that has the pi bonds, the oxygen, it's going to keep that positive charge there. And it also has better yields. FC acylation is more like a 75% yield. So measurable yields, no rearrangements, a lot more predictable. You just wind up with this pesky carbonyl attached to the benzene ring, which you might not want for synthesis purposes. So deciding between these two, if we're trying to get to an alkyl group added to benzene, it's always sort of a balancing act. How hard is it going to be to get rid of the carbonyl at the end versus how much rearrangement am I going to have and how bad are the yields here? And it depends a little bit on a case by case basis. And the other aspect of it is the alkylation only works with sp3 carbons. So if you, I guess it says 66% yield, that's higher than I thought it would be. So 2-chlorobutane is not going to rearrange, so we don't need to worry about that. We get 66% yield. 1-chlorobutane, we're going to get a mixture of the two products. And not necessarily predictably. We would think that the carbocation more often than not would rearrange to do this, but because we have that aluminum chloride complex forming to begin with, it stays like this a little bit more often than normal.
But not often enough that you're not gonna get a greater than 50% yield on either of these, because you're taking that 66% and splitting that somehow. And then the other aspect is if you try to do this on an sp2 carbon, it winds up not working. And so either if you have vanilla chloride or a phenyl chloride, neither of these will react with this mechanism. So we can't use this as a way, if this would be kind of handy, it'd be a way to attach two benzene rings to each other. That is a molecule that exists, but it's not super stable or easy to make. It seems like you would expect it to be relatively stable. Except that resonance that you might get there across there, you actually wind up with an even number of electron pairs doing that. And it's not really a ring structure, so it's not truly anti-aromatic, but it's also not, it's non-aromatic. What we actually see with this is actually the two pi bond or the two benzene rings are perpendicular to each other or close to it.
So the two electron clouds are repelling each other.
Basically, yeah. If they resonated, we would get something resembling anti-aromaticity. And so to avoid that, it just rotates them. So that's probably one of the reasons why we don't see this working, but this doesn't work either. Which that's a little bit surprising. But yeah, just the nature of the way these pi clouds interact, this doesn't get turned into as good of a Lewis acid. No, Lewis base. This is not as good as Lewis base as an alkyl group. Unless the chlorine is attached to a carbonyl. Right, having chlorine attached to a carbonyl gives us the acylation. I'm preemptively fixing the figure here before I switch to the next one. Again, same step, generating your electrophile. It's just your electrophile is a carbon with a positive charge, that acylium ion. That works because we get this resonance. We can't have this resonance structure if it was a vinyl group, if it was an alkene, because we don't have any lone pairs on the adjacent carbon in that case. In this case, we get a little bit of resonance because that oxygen doesn't really want to share, but it gives it just a little bit more stability. So we see the acyl group reacting to make an acylium ion, which then acts as a nucleophile. Carbon, or sorry, electrophile. I keep doing that out of habit. So we've talked about nucleophile so much more. The carbon acts as the electrophile. And we make our sigma complex. And leaving group leaves, we reform our aromaticity. Yeah, and again, these steps are the ones that are a little bit trickier, just because there's more to remember with all the different types of nucleophile or electrophiles. Again, making sigma complex is easy, and then leaving group leaves. So if we have an alkyl group already attached, that's an electron donating group, slightly. That means where we put the other electrophile becomes important. If we put the other electrophile either adjacent to it to make our sigma complex, we do that, that doesn't necessarily look like it makes any difference, but think about all three resonance structures. So there's a resonance structure that puts the positive charge there, directly next to an electron donating group. So it makes it look like a tertiary carbocation is one way to think about it. We're used to thinking about carbocation stability. That means that putting the chlorine in this position allows us to make a slightly more stable sigma complex. If we put the chlorine here, now our positive charge is there. It doesn't matter how we resonate these. If we drop all three of these resonance structures, none of these resonance structures is going to put the positive charge there.
So the meta.
So the meta position doesn't work
Yeah.
if your substituent is electron donating. And electron donating substituents will actually increase the rate of reaction slightly. Because you're making this, by making one of the components of the sigma complex more stable, you're making the whole sigma complex more stable. Because really it's a linear combination of all three of these
Right.
orbital sets, right? So by making one of them more stable, you actually make the whole thing more stable. Electron withdrawing groups are going to do the exact opposite. Electron withdrawing groups are only going to go in the meta position because you don't want to put a positive charge next to an electron withdrawing group. And electron withdrawing groups are going to slow the whole process down because if you have an electron withdrawing group on this benzene ring, there's less of a target for an electrophile, right? Just in terms, think about an electrophile as something seeking out electrons. By pulling electrons away from the benzene ring, you make the whole benzene ring a less attractive target for an electrophile.
Yeah.
All right, and we have a whole lecture on Thursday that's practice with that. The whole lecture on Thursday is just, here's what we do if it's already substituted. If we're making a di-substituted benzene. Here's the process. Right, but just so that you've seen it once and you understand and can marinate on that logic. Where is this one? So they refer to these as directors. If it's an electron donating group, is an ortho-para director. Because it's going to preferentially direct another electrophile into the ortho or para position. And ortho-para directors are activators. In anything with a lone pair, either an alkyl group or any lone pair adjacent, the benzene ring is going to be an activator. It's going to be an ortho-para director. Anything with a pi bond conjugated with the benzene ring is going to be a deactivator. Is going to be a meta director. And it's because having even something as electronegative as an oxygen, it still has a lone pair that can donate electron density and resonate into the ring. Putting a pi bond here, all the resonance structures you can draw with that pi bond are pulling electron density away from the ring. And again, we'll go over this again. But I just want you to see the different possibilities. So here's the whole figure. Again, too big for it to fit. You have strong, if you look at all of the deactivators, with the exception of halogens, halogens are deactivators. Even though they have lone pairs, they're the exception. Everything else down here is pi bonds and electron withdrawing groups, or highly electronegative groups. Everything up here is lone pairs or other ways of donating electrons. All right. Let's end there for today. And on Thursday, we'll spend more time with that, more practice drawing resonance groups and we'll start with a review of these reactions just to come back to them and think about it again. All right. Make sure you put some shoes on before lab.
Oh, for sure, okay.
Just before I forget.
Oh, yeah.
I thought about wearing sandals today too, and like, no, I can't, I don't get to do that. And yeah, and today in lab, we're gonna make a Grignard reagent, and then next week we'll use it.